the Cartesian velocity. Okay, when I say Cartesian velocity, it's basically x dot, y dot, z dot. Okay, so here's how you do it with theory. Okay, so if you have R, or let's say P, is some point of interest, and we have computed the position of that point in frame 0. So we did this for the double pendulum. We found a position of G1 and G2. So we got that. It is going to be a function of Q, right? Q is the degrees of freedom. So in the case of pendulum, it was θ1, θ2. In global frame joint angles. Okay, now we know the definition of Jacobian here is df dq, right? So I'm going to rearrange this and write it as df equals j dq. Okay, now I don't lose anything if I just divide by dt, in which case when you divide by dt, it becomes the absolute derivative. So it's not a partial anymore because f is not a function of time. Okay, but what is dq dt? It's basically, here it's going to be the angular speed, angular velocity. So that's only for the pendulum, right? If it is a system which had linear motion, then it's going to be linear speed also. And then f is, so it's, what's f? F you can see is it's right here. It's basically gives you the position of the point. So this is like saying, what's the derivative of f or the derivative of p? This is nothing but p dot 0. But p dot 0 is nothing but the rate of change of position, which is the linear velocity. So this is the velocity. So in other words, if you see this expression, which is very common in most textbooks, it says v equals j times q dot. It basically is telling you what the linear speed is, or Cartesian speed is, given the angular speed or the velocities of the link of the individual links. The relation between them two depends on the Jacobian, which is df dq. Okay, so let me just show you one thing about this with respect to the double pendulum, and then we stop. So we've computed the velocity of G1 and G2. We go back here. So we've computed the velocity of G1 in frame 0 as C1 cos θ1 omega 1, C1 sin θ1 omega 1, right? We got this by differentiating xg1 and yg1 with respect to time. So the claim here is that you can get the same answer if you use the expression which I wrote down, which is v equals j times q dot. So I'll write it that way, and then we can check with this. So example. Okay, so we have velocity of G1 in frame 0 is the Jacobian of G1 times q dot, okay, where q dot is the angular speed of the links. In this case, it's going to be θ1 dot, θ2 dot, or omega 1, omega 2. Okay, so let's compute jg1. It's the rate of change of f with respect to q, where I need the positions of the link of point G, right? So for that, I go again here. I need to compute xg1 is here. So xg1 is this, yg1 is that. So c1 sine theta 1 and minus c1 cosine theta 1. So I write that down. Okay, so when I take the derivative with respect to q, remember it is df1 d theta 1 df2 d theta 1 df1 d theta 2 df2 d theta 2. Okay, so df. So let's look at each of those terms. df1 with respect to d theta 1. So this is f1, this is f2. So if I take the derivative of first term with respect to theta 1, okay, so here you treat everything else except theta 1 as a constant. So that derivative is c1 cosine theta 1. Then I need to take f1 with respect to theta 2. So you see that it's not a function of theta 2, so it'll be 0. And then we have df2, which is this with respect to theta 1. So it's minus c1 sine theta 1. So derivative of cosine is positive. It's a negative sign, so it's positive c1. And then this has no theta 2 in it, so it's 0. Okay, so if you put it all together, that is here, we can write this down as jg1 is c1 cosine theta 1 c1 sine theta 1 0 0, and then q dot is theta or omega 1 omega 2 sorry, it's omega 1. Okay, so we have this expression, which we can check with. So it's c1 cosine, c1 sine. Let's check that with what we had. It's the same thing here. It's the same thing. So you get the same answer. Now, what I would recommend is you can try this on this. So I don't have time, so I'll just put it down. You can try, check this. Also check PG20. Okay, so check, do the same thing, same formula I wrote down the way I did it for VG2, and check this answer with what you get for the second link, which is this expression. You got to check this, okay? Okay, so velocity of G2 is the Jacobian of G2 times Q dot. Okay, so that is Tx G2 in frame 0. Here the variables are theta 1 and theta 2. So that will be T theta 1 and then D y G1 in frame 0, T theta 1. Tx G2 with respect to 0, and we take the derivative with respect to theta 2. And then we have theta 1 dot, theta 2 dot. Okay, so when we simplify this, so xg1, xg2, and yg2 were defined earlier, they should be somewhere here. This is the derivative x. Okay, right here. So this is xg1 is the top line and xg2 is the top line, yg2 is the bottom line. If you need to take the Jacobian, so the derivative of that with respect to θ1 and θ2. And so when you simplify it, you get so I think I defined this as omega1 and this as omega2. So we can write this expression as omega1 C2 cosine θ1 plus θ2 plus L cosine θ1. So that would be 1. And then the other one would be omega2 C2 cosine θ1 plus θ2. And the second row would be omega1 C2 cosine θ1, sorry, sine θ1 plus θ2 plus L sine θ1 plus omega2 C2 sine θ1 plus θ2. Okay, and so this is velocity in frame 0. Okay, so that's the first application. Here's another application of